in your data center, you want to deploy it. So basically today, I want you to learn how to do it manually. Okay, so day one, manual HPC cluster installation. So just where am I? Because you can see my face, so it's not very fun, but I am located in France, at very, very west of France, in Bretagne, at Auray, a small town, okay? So at least you know where I am today. So as an introduction, I would like to say that it is a best effort training, okay? I didn't add a lot of time to prepare everything. I wasn't given a lot of time. So I did my best. There might be some mistake. I would like to thank everyone who helped organizing this training. And I hope you will have fun and enjoy this training, at least as fun as I had to prepare everything. A big warning right now, okay? We are going to do a lot of stuff today. Don't do that on a production cluster, okay? What we're going to learn is to do everything manually. Don't try anything today on a production-ready cluster, okay? Practice before, so at least. Okay, so this is the philosophy of this training. I like to remember this sentence, okay? Give a man a fish and you feed him a day. Teach a man to fish and you feed him for a lifetime. This is why today we are going to focus on practical session mostly, okay? I want you to practice today to do a lot of manipulation yourself. So you know, you remember, and when you come home, you can do things yourself, okay? So what I want you today is to create the most generic HPC cluster ever, okay, manually. It's like if I ask you to create a car, okay, but just I want you to create the most simple car, like a kid will do a car. So you create the car with everything simple, the motor, the wheel, etc., but just very simple. And I want you to do it manually today, okay? So no tricks, everything under the hood, so you understand how it works exactly. Tomorrow, we will learn, not tomorrow, but next week, we will learn how to automate everything you have learned today, okay? But today, everything will be done manually. It's very important to understand and feel how it works exactly. So here is the timing. First part of this day, we will have a small, a big time on vocabulary to understand all the concept. It's not very vocabulary, it's vocabulary and concept, okay? Then I will explain you step by step how to set up and deploy an HPC cluster manually, okay, from scratch. And a few small parts will be dedicated to migrating from HCL 7 to HCL 8, because maybe you already have a cluster running in HCL 7 and you want to upgrade. The next day, so it will be next week, Monday, Tuesday, it will be Tuesday, we will learn Ansible. Okay, you will see that Ansible is an automation tool to deploy things automatically, to push we call it provisioning. Okay, so you're going to provision your cluster because you don't want to do every time the steps manually. For example, if you lose a server for hardware issues, you don't want to redo everything manually. So you will learn how to automate things. Okay, and last day, I will show you how to set up a cluster fully automatically using an open source stack. And also we will have a small part regarding monitoring, because monitoring is essential if you want a production cluster. You want to know what's going on your cluster. You want to be, I would say, the cluster is going to be your baby, okay? And you want to take care of it. It must be each time running in perfect shape, okay? So I want you to be a true sysadmin hero, in fact, okay? Each day you will learn a lot. That's okay. Okay, so let's start with the vocabulary. If you have any question, okay, I see you, at least you don't see me, but I see you. Don't hesitate to ask. I will stop and explain everything, okay? Also, sometime I will stop the PowerPoint and I will show you things inside a shell like this, okay? So you see exactly how it works. So let's start with part one, vocabulary and tips. So let's be in synchronization with vocabulary. So what is high performance computing? It's everything that goes well beyond normal computing usage. So well, you can say that everything that cannot be done on a standard computer. I would say that doing calculation on a very big workstation is still not HPC. Okay, it's still computation, but not high performance computation. Okay. And what is an HPC cluster? It's an aggregation of a lot of bare metal servers. You will see that it is very common in HPC that we use bare metal equipment. We don't use VM. We don't use hypervisor a lot because we want to have the most possible performances available. And you don't want to add layers that will reduce performances. Okay. However, it is very common to use containers because containers do not impact performances. You have direct access to the hardware. So an HPC cluster is an aggregation of bare metal server. It's also a high performance network. If you have, for example, METEO calculation, you want to share data between each chunk of on the grid. So you need a lot of exchange over the network for everything to communicate. On the other hand, if you do 3D rendering, for example, you don't really need a high performance network. But basically, on most HPC cluster, you will have a very, very high performance network. Also, what you're going to need is a fast and large storage. You will see that most of your users are, I would say, dirty users. They will tend to use a lot of space, copy a lot of data, and don't remove them. So you need to take care of your storage. So first, let's start with the hardware. Don't worry, by the way, I will provide you all the slides when everything is finished, okay, in a PDF format, so you have everything. So what is a cluster made of? I tried to draw a very simple cluster, so at least you have some kind of view of everything, okay? So we will use this schema a lot. So first of all, you have what we call a management node. The management node is, I would say, your very most important server. This is where everything is centralized. So your job scheduler, everything that deploys on the node, your monitoring, your users authentication, everything is most of the time centralized on your management node. So this is your most important server. Most of the time, you don't have only one management node. You will have multiple of them. And we are going to use high availability mechanism. So in case one fail, it will fall back on another one, etc., etc. Okay. So here in this schema, you only have one, but most of the time you have multiple of them. Then you have the login node. So the login node is where your users are going to interact with your cluster. The login node is a very, very special node. It must be always up to date with security fix because it is where your users are and it is where your cluster is vulnerable. Okay, you have to take real care of this node. It must be extremely simple so you can upgrade it nearly each day. Okay, so the login node is connected to the web and sometime to a firewall between the web and the login node. Okay, so this is where your users are coming from. They connect from the web through your firewall and reach your login node. And they will interact with your cluster from the login node. Okay, they should not be allowed to go somewhere else. Then you have the storage node. We call it also IO node. Okay, this one is to provide, I would say, centralized storage for the whole cluster because on each node you're going to deploy the operating system on the local disk, but the main storage will be shared across the network. So each node has the same data, and for example, users have access to their data on each node. It's important for synchronization. For example, the user is going to build their code on the login node, and when they want to launch it on the compute node, if the code is not available, if the binary is not available, the compute node will not be able to launch it. So the data are shared across the whole network using a dedicated servers. Okay, so most of the time you have multiple storage nodes to provide very fast storage. Then we have the compute node. So it is a very basic element. Most of the time you don't install a lot of stuff on them. You want them to be as light as possible. Also a small tip, you should disable the swap on the node. Okay, so try to keep them as indestructible as possible and as simple as possible, because you want to have the maximum resources available. It's like if you have a Formula One car, you are not going to put inside, I don't know, something very heavy that will slow it down. Okay, so these are the compute nodes. There are multiple kind of compute node. The most common are CPU node. Okay, so there are the very simple one with 1, 2 CPU. Okay, you have the GPU node. There are more and more common. Most of the time, these are NVIDIA GPU node. I created them here on the schema a little bigger than the CPU node because they are most of the time bigger. Okay, a GPU is a big element and it uses a lot of power. So the GPU node are most of the time bigger than the CPU node. And last but not least, you will not see them each time in each cluster, but you have the SMP, or what also we call fat node. Okay, the SMP node are very different than the two others. Let's take an example. When you do biochemistry, okay, when you do molecular imbrication to create vaccine or medicine, you need to use a lot of memory, okay, to have your molecule vibrate and try to find the best match to create a new medicine. But all of this stuff needs to share the same memory. I mean, you cannot do this kind of calculation over the network. So for this kind of calculation, you're going to provide an SMP fat node. It's a very big server, okay? Most of the time it's like 20 server size, and it has a lot of CPU inside, a lot of memory, but everything is aggregated as a single host. So from the Linux operating system side, you just see one system with a lot of CPU, a lot of memory. So users, when they launch a calculation on this kind of node, they don't have to take care about network or anything because their algorithm, the algorithms they use cannot use the network, cannot be splitted on the memory side, but it works on this kind of node. Okay, so it's not very common, but for specific usage, you will see SMP node. Regarding the network, no. Basically, most of the time, you will have Ethernet network, 1 gigabyte. It's very standard. Today, we more and more see 10 gigabyte network, but to be honest, it's not very useful. You just need 1 gigabyte because the Ethernet network here is made to deploy operating system, is made to upgrade system, to push configuration, to grab users, authentication, etc., to do the monitoring. But after that, all the data, all the computational part are done on the interconnect network. This is your fast HPC network, the interconnect network. Okay. Most of the time, it's called InfiniBand because there is only one big provider over the network. It's called Mellanox. For the small story, Mellanox was just bought by NVIDIA. So NVIDIA is coming a very big company because they bought ARM, they bought Mellanox, so now they are very big. Okay, so most of the time it's going to be InfiniBand, but sometime you will also see Intel interconnect or Cray interconnect or Bull BXE, but they are not very common, but most of the time it's InfiniBand from Mellanox. Okay, so now let's focus on, yes, you have a question?
I didn't get the interconnect very well.
Yeah, okay. Let me explain you. Yes, give me a few seconds, okay? I will show you exactly how it works. I think it's better. Give me a few seconds. I need to stop the sharing. Okay. I will show you in real life how what it is like. Okay. Give me a few seconds. I need to connect to a cluster. Okay, and this one here. We are here. Okay, let me increase the size. Okay, which one is available? This one. So here, see, I am on a compute node called Ion 00001. Okay, if I check the network available, I have my Ethernet network. Don't take care about the loopback;
But
it's
not,
internal stuff. Okay, I have.
we can we can see what you're sharing.
You don't see it?
Yes.
Why? Okay, let me share the screen again. It seems it's just disabled. You see now?
Yeah. Yeah, we can
Okay,
see it now.
nice. Okay, so I am on a compute node called Ion 0001. Okay, this compute node is connected to two networks. Ethernet network here. Okay, so you can see it's a very simple Internet device with IP. And I have something called IB0 here. This device is very special. Right now it's done. Okay, anyway. It's called an InfiniBand device. Okay, you can see here also. It's not Ethernet like here, it's InfiniBand. The InfiniBand is a very specific network. It's kind of an Ethernet network, but it has very big bandwidth. Okay, so if you want to send data over the InfiniBand, it's like instant, and it has a very low latency. Okay, so let's take an example. Um, I want to do Meteo calculation. Okay, so I take Africa, the whole Africa, because I am Mr. Africa Meteo. I want to simulate the weather across all Africa. I take the whole Africa continent. Then then I want to do some physics calculation over the whole Africa, but I cannot do all of that into a single computer. It's impossible because it takes too much resources. I mean, the grid I will need is just too high. Okay, so I'm going to split Africa into a very small chunk. Okay, not one chunk per country. Very big, very small chunk, like the size of a village. Okay, and I will ask the HPC cluster. Each compute node is going to take one small chunk of the whole Africa, and then all together you are going to calculate the weather. But to do that, each each compute node, each server is going to need to exchange data across time with all the neighbor. Okay, because for example, if I am in the village 1, which is close to village 2, um, when compute node 1 is going to calculate the weather in village 1 at time 1, it needs to exchange with village 2 the data, the neighboring data, because if there is a storm in village 2, village 1 need to know that. Okay, so they will exchange data over the network. But if I exchange over this internet network, it is too slow. I have a big latency. So my CPU is going to wait for the network. You see what I mean? The CPU is going to calculate the weather locally, then wait for the network to send the data. And you will lose a lot of CPU performances, a lot of CPU time. However, if I use the InfiniBand network, it's nearly instant communication. So you don't lose time doing communication over the network. You see what I mean? I should have prepared a schema about that. I know. I will try to prepare one for next day. Okay. So basically, the interconnect is a very, very fast network that is designed to ensure your CPU are not waiting for the network. Simply. Okay. Because when you do calculation, when you do parallel computation, your physical, your mathematical stuff need to share data over the network, and you want something very fast. I hope it answered your question. Okay.
Yes.
Okay, cool. You still see my screen?
Yes.
Okay, thanks. So now let's focus on one node, one compute node, but any node in fact. Okay. So let's open it, and what's inside? So inside we have the motherboard. Okay. You have the power supply unit called PSU. So there are, for each vendor, there is a specific shape. Okay, you have the CPU, central processing unit. You have the memory, random access memory, the storage, okay, disk, SSD, whatever, and sometime a GPU, graphical processing unit. So let's focus first on the motherboard. On the motherboard, you have, well, few elements. We are not going to go very deep in details, okay? I just want you to understand basic concepts, and that's all. Because as an HPC admin, you will have to go onto the field and change, replacement, change part, replace element, because there will be failure all of the time. So you have the socket here. It's where you put your CPU. Okay, be extremely careful with the socket. It is a very, very fragile element. Well, in my life, I already lost like 10 sockets. Okay, it's very, very fragile. So be extremely careful with the socket. Then you have the memory slot. It's where you put the memory. You can see here, it's interesting because we will discuss that later, that you have memory slots for each socket. They are grouped. Okay, we have grouped with one socket on 8 memory slot here, on the same above. You have the PCI Express slot, okay, on the left up. So it's where you're going to connect your GPU, your interconnect like InfiniBand or your Ethernet card, etc., etc. And now on the bottom side of the server, you have the Ethernet slot, like on each equipment, USB, etc. But you also have a very specific slot here. I don't see. You see my mouse moving? Yes. Okay, I hope so. There is a small Ethernet port called IPMI, dedicated port.
Benno, we
Yes.
see your mouse moving.
Okay, thanks a lot. So this port is very important, okay, because it's called BMC, Board Management Controller, okay. You're going to use it a lot because when you are remotely deploying or interacting with your equipment, with your server, you need a way to remotely power them on, power them down, reset them, check, reach the BIOS. You don't want to go on site each time to plug a screen on a keyboard, etc. You're going to do everything remotely. And this is done using the BMC. So there is a very specific port here dedicated to what we call a BMC. So here, for example, you have your motherboard, again with CPU, socket, memory, mainboard, and you have this small board inside, embed, connected to the BIOS of the motherboard, called the BMC. The BMC is in fact a very small board, autonomous. Okay, it has an operating system. It has a web page available. It will connect on the network. It will get an IP for its own, so not the same IP than your server, for example. And you're going to interact with it to check the health of your server, to reset it, etc., etc. Also, have a look here. There is something between the two CPU called QPI or Hyper Transport Link. And it's important to understand that when you have two CPU in a motherboard, it's not like one big CPU. You will see that most people think, well, I have two CPU with 10 core. It means that I have a big 20 core CPU. No, that's false, completely false. Because when you have two CPU, there is a specific link between them, but this link has a very high latency compared to direct access, for example, to memory. So if you have a program executing here on the CPU, on the bottom CPU with memory located in the RAM of the upper CPU, performances are going to be very bad because each time you want to access the memory, you need to cross the QPI HT link, reach the other CPU, and get the memory on the other one. Okay, so don't be fooled. Remember each time for your user, explain them that it's not like a big CPU. You have to take care where you put your process and where you put your memory of your process. It's called binding memory. Okay, so be careful with that because most users don't know that. And they will launch calculation on processors and they will have very bad performances. They will don't understand why. It's just because their memory are not on the good socket. Okay. So we are going to use the BMC to communicate with the board to power off, blink, console, etc. So one of the most common you're going to use is IPME tool. Here, for example, I say, okay, I need to power off my server. Okay, so let's have a very specific look here on the right with the LED. Okay, you have the status LED, so I will show you them later. You have the power button and the reset button. Okay, so with IPME tool, I want to also, this is a command that is going to use the network. So the BMC network we have seen before over the Ethernet, and we are going to communicate with the BMC to ask, okay, now I want to stop my server. So I will do IPME tool -H, so host. This is the name of the host of the network, so C0001 BMC. -U and -P, it's password and user, so there are some credentials to protect the BMC over the network. Of course, you have to change the default one. -E LAN plus, it's just a way to reach it. Then I say I want chassis, so chassis it means the server. Power statue, I want the statue of the chassis. Right now, you see everything is powered down, so it will answer chassis power is off. Then I want to power it on. So IPME tool, same, chassis power on. I just need to wait a bit because it's not instant. And then the system is going to power on. Okay, you will see the LED powering on. So if I again do a chassis power statue, it will say no, power is on, chassis power is on. Okay. So you see the green light here. Okay, now I want to power it off again. IPME tool, chassis power off, sleep a bit, and then it will just power off. If I do a chassis power statue, chassis power is off. End of the deal. Very simple. Okay. Now let's say I am the HPC sysadmin. I am the mighty HPC sysadmin. I don't want to move from my chair, but I know I have a friend inside in the room, in the IT room, around the server, and I am on the phone with him, and I say, "Hey, dude, I want you to check the server C0010," and the guy will tell you, "Hey, which one is it? There are like 100 of them, 1,000 of them. Which one is it?" You're going to use this command to say, "I want to identify the node for someone on site. Chassis identify force." It will make the blue there is some kind of convention, okay? It's a blue LED. A blue LED is going to blink on the server you want to identify. So the guy on site can go check which node is blinking blue, and then he knows which one, and he can work on it, okay? When you want to stop it, you do chassis identify 0, and it will stop. Okay, so force to make it blink, 0 to make it stop. If you remove the force, if you just ask chassis identify, the blinking will only be for like 15 seconds. It's not very useful. So force is good to make it infinite, but remember to stop it when you have finished. So few other things interesting. You can reach the console. The console means you can see what's on the screen of the server, even if there is no screen plugged. Okay, so let me show you this. For example, you still see my screen, I hope. It seems to be, yeah, you see it. Okay, cool. For example, here, you want to reach the console of this node. And now you see I am on the console itself. See, this is what I should see on the screen. It's not an SSH. This is what, if a user plug a keyboard on a screen on the server, this is what they will see. So I can log in, and I am on the system. So it's not the same thing than, for example, SSH, which is different. Okay, here I'm using the network to reach the system. With IPME tool, I was using where is it? This one. I was using the direct console of the system. Okay, you should also use this small parameter. Okay, so -e /e commercial. It means that because it's difficult to exit a console, you will see it's not that easy. It's very, very old stuff. I don't understand why today we still have to deal with this kind of very old very old things, but at least, well, this is how things work. So you're going to say, okay, I want to use this escape parameter, this escape key. So to escape the console when you are inside, you are going to press enter, then E commercial, then dot, and it will exit the console. Okay, simply put. If a console is already active, sometimes someone left the console open for anyway, you just deactivate it. The IPME tool, blah, 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 sol deactivate, then you can activate it again and reach it. Okay, also be careful, the console need the output to be redirected to the server console. So by default, the BIOS is in the server console, the PXE boot also is in the BIOS console, but once your Linux kernel is booted, you will see nothing, except if you add on the console command line, okay, the matching hardware Linux kernel, the matching console. So the vendor should provide you that. Okay, for example, in my example, here again, if I SSH that, you can see this is what was given to the Linux kernel at boot, and you see this. This is the console parameter for this equipment, for this very specific hardware. And this allows me to see the Linux kernel over the IPMI console when the system is booted. So be careful. If you don't put this, you will see nothing over the IPMI once the Linux started to boot. Okay, but this is dedicated to each hardware. So you have to ask the vendor, Bull, Dell, HP, whatever, Cray, what is the good console to use. Okay. A few other stuff very quickly. Cell list. It allows to see the BMC event log. So memory issue, CPU failing, PSU failing, sensors issue, overheating, whatever. BMC current network setting. If you want to see the BMC network setting, what is the IP, VLAN, whatever, LAN print 1. To see the sensors, maybe you think system is overheating, you want to check that. SDR list. And to reset the BMC, just MC reset code. Okay. So let's focus now on the power supply unit. Well, you have already seen that with Tom yesterday. So basically, it's just a very simple transformer. You have the primary transformer and the secondary part. Okay, so let's not go into detail. I just want you to be very careful because as a sysadmin HPC, you are going to go a lot of time on the site, plug cable, remove cable, do stuff like this. You want me to slow a little? Yes, okay, no problem. Okay, let me slow down a bit. So when you go on site, you have to be extremely careful because the equipment you are going to interact with are dangerous. And sometimes it's not clearly explained. Okay, for example, 1 year ago, one of my colleagues went on site just to plug an Ethernet cable and he touched something that shouldn't be touched. And he had a very big surprise. Okay, so if you go on site, if you touch equipment, be extremely careful. These are very dangerous equipment. For example, one of our equipment, the Sequana 2, when you go inside the equipment, we have more than 100 ampere continuous voltage at some point, and these points are not protected. So if you put your finger inside that, you're dead. That's end of the game. Okay, so be extremely careful with the equipment you handle. This is a very big warning because sometimes you are on pressure. Your boss wants the production to be ready on time. You don't care. Okay, life is important. So be extremely careful. This is a big advice. Even if you are a software engineer, you will go on site, plug things. Be careful. Okay. Also, another very important tip: when you go on site, most of the time you will shut down the power to intervene, to do manipulation. But it is very common that someone else comes, hey, my server is done. Who did that? And we plug the power on again, and you're dead. So when you go on site, and when you want the power to be done, lock it. Okay? Be careful. Lock the power and ensure nobody put it again. It may seem funny right now, but I assure you it's very common. And I have seen a lot of guys going to the hospital due to that. So when you go on site, when you do manipulation, lock the power. Be careful. Okay, let's move to the storage disk now. So there are a lot of kind of disk available on the market. The most common one are HDD, SATA HDD. More and more we see SSD, okay, to handle the compute node or equipment. And more we see diskless, means that your server do not have storage. So you're going to load the whole system into RAM memory directly. What is interesting with diskless is that it uses less power. It's not sensible to earthquake because HDD don't like earthquake. So in some countries, it's very important. It resists failure because when you reset the node, it is a fresh operating system. Okay, so no issues. It's better for security because when you reboot, the system is no more compromised. But on the other hand, it can be a very big pain because nothing is persistent most of the time. So when you do manipulation, if the node reboot, you lose everything. So you have to weigh pro and cons, okay? But it's very common to see diskless now. It's cheaper, of course. Let's see the RAM memory now. So there are two kinds of memory on the market. You, on your computer right now, on the laptop you have on your table, I see right now, you have non-ECC RAM memory. Means that it's very standard memory without error recovery. On all HPC server, you have ECC RAM. So don't try, for example, to put the RAM of the server into a workstation. It's not going to work. The ECC RAM is different. It has one more slot, one more memory inside, one more chip, and it is here to check if there is an error or not. When it's doing calculation, for example, the data are stored here, and if there is a small error, the ECC mechanism is going to recover it. So when the operating system says, okay, look, I just recovered from one error, it's okay, it's normal. But if the operating system say, look, I am always recovering for error like 10 times per minute, you have to change the memory, it's broken. The CPU processing unit, central processing unit. So it's very, very strong element. It's very rare that you break a CPU. Contrary to the socket where it belongs, the CPU itself is very, very strong, very difficult to break. Okay. When you remove the IHS, you have some kind of grease thermal paste, and you see the die. We call it the die, the chip itself. Okay. Here is what a die looks for. So this is it is not a professional die. It's a very common die. Oh, you want to how to identify a specific faulted memory module? Yes, good question. Simple. Well, first you can use this. Where is it? If you want to check a memory error, come on. Here, when you do the when you check the BMC event log, it will display if there is an error in memory or not. But also, very small tip, you can do that. I'm sure we will have one. The message. But I'm sure we will have some error. Okay, it should be faster. Come on. Okay, do we have an error somewhere? Yeah, this one, very nice one. Yeah, you see. So dmessage, when you type dmessage, D-E-M-S-G, it means I want to ask the Linux kernel to display all the event log. And when you check the dmessage for error, sometimes you will see this. Corrected error, no action required. It means that the ECC mechanism just corrected an error, simply. When you see no action required, it means it's okay. The system handled it, recovered it, and that's all. But if you see them too much on the same compute node, you should consider replacing the memory. Okay, so that's a very small trip. Just do dmessage grace rep minus e error, and it's kind of compatible with all system. You will get the error. So clush, you will learn it later. Clush means I want to spread over the whole network a command. Okay. Where were we? This part. Okay. So this is a die. So how the CPU is made. You have, well, don't care about the GPU. It's only for standard laptop or stuff like this. So you have the CPU core, you have the interconnect ring, you have the memory controller, and all the stuff. You can see here that a CPU core is extremely complex element. You see, it has a lot of small parts. So a CPU core is very complex. It is able to do complex calculation. So let's take a small look on what is inside a CPU, a core. Okay, you have a very interesting part. So, well, don't care about all of this. I didn't have time to go deeper in this. Okay, we don't have enough time. But anyway, what is interesting for you as an HPC sysadmin is this part, the execution engine here. And there is something you need to take care, something you need to understand, is what we called single instruction multiple data. When a data, when you do some calculation on the CPU. There are two ways to do the calculation. Okay, you can use the, I would say, basic units. So int ALU, for example. So this one is going to do all the integer calculation. So 1 plus 1, 1 plus 2, etc. So it's called scalar operation. And you have another unit called int vect ALU. It's one what we call single instruction multiple data. So how it works? If you do the calculation, let's say I have two matrix, two scalar, two addition, two sum. Okay, so I want to sum the scalar. I want to sum vector A on vector B. So a vector is a table. Okay, I want to sum each element. So A plus A0 plus B0 equals C0. If I use the scalar unit, it will take 4 cycles to do the calculation for this operation. Okay, 4 cycles. So if I operate at 1 gigahertz, for example, you can do the math, how much time is going to need to do the calculation. If I used this unit, int vectorial unit, so it's called single instruction. I have one instruction, it's the same instruction, multiple data. I do it on multiple data. So in one cycle, one cycle of the CPU, I will do the whole calculation. So 4 calculation in one cycle. If we consider it as a stream, it can also be seen this way. You have the instruction on the way, you have the data, and with a scalar system, it's going to be kind of slow. When you have a very big SIMD, you do a lot of more with the same instruction. So it's only if you have calculation that do the same mathematical operation, but a lot of time on the same on very big array of data. And you will see that in HPC, it's very common. For example, again, Meteo, when you do the Navier-Stokes equation resolution, let's say you want to sum temperature and pressure on the field to calculate, I don't know, velocity, whatever. You are doing a very big calculation over the same array to calculate for each small element of the grid the same data. So you are doing to do the same operation on each element of the grid. So in this kind of calculation, the SIMD instruction will dramatically improve the performances. So just for you to know that it exists, and it is what we called, well, Intel like to show off about that. AVX, FMA, all of this very big name. It's in single instruction multiple data, in fact. Okay, let's finish with the GPU. So most of the time it's NVIDIA. Okay, don't be fooled. Well, it's always NVIDIA everywhere. It's not like I like them. It's just that the way it is. They are everywhere. So a CPU and a GPU are not very similar. Okay, you can see that a CPU has very big core. On the other side, a GPU has a very, very small core. This is a core here, okay, a very, very tiny one. But you have a lot of them, very, very big amount of them. So in fact, a CPU can be seen as a slow amount, a slow amount of big cores. On the other side, a GPU is a very big amount of very small cores. Okay, so this is how a GPU is made. So you can see that here in my GPU, I have a lot of small cores. And the GPU cores are only, for example, 32 bits, while a CPU are 64 bits, etc., etc. So it's not the same target of calculation. So you may wonder why the GPU are made this way. It's because of video games, simply, okay? Because the GPU were designed for video games at the very beginning. And one of the most example is anti-aliasing. If you have played a video game once in your life, you know that a lot of guys like to not see the small aliased stuff, so they apply very big filters, and it takes a lot of calculation power. Same here. Okay, without aliasing, you do have this, and with aliasing, you have this, etc. So a GPU is made basically to do this kind of calculation. You have a picture, and you want to apply filter on it, a lot of filters. And these filters are applied on each pixel of your screen, which means you need a lot of small processor, a lot of small cores to calculate simply each pixel. Okay, that's why a GPU is made of a large amount of small cores. It's just to handle a lot of pixels, but with very basic operation, very basic geometry operation. That's all. Okay, so you can see a CPU as a big, I would say, big stuff. Okay, very complex, very unbreakable, and it can do a very complex operation, but just one. Okay, and on the other side, the GPU, you can see that it's kind of a colony of very small cores that work together to achieve a common goal. Okay, to achieve a very specific stuff. So if you use a GPU to do a CPU dedicated task, you will get like very slow amounts of power. Same. But if you use a GPU to do a GPU dedicated task, the power is insane. Okay, let's be clear. If you do graphical calculation, image calculation, meteor on a GPU, the power is insane compared to a CPU. It's like 100 more efficient. It's incredible. So the GPU are very powerful, but they are not designed to do everything. On the other side, the CPU can do nearly everything, but slower. Okay, that's all for the hardware. Now let's focus on the network. So you have the Ethernet network. So as I said, it's used for administration and simple exchange. It's used to deploy the operating system, to deploy package, to manage very native services, the time synchronization, name resolution, etc., and to manage the BMC, the board controller. It has, as I said, a high latency, like 100 microseconds, and low bandwidth. Okay. On the other side, you have the interconnect. So it's used for storage, it's used for scientific programs to communicate. It has a very low latency, like 1 microsecond. So Ethernet, the best Ethernet, 10 gigabyte. It's like the Ethernet of King, 100 microsecond. Okay, InfiniBand, 1 microsecond. You see, much better, and it has a very high bandwidth. Also, you have to understand that an InfiniBand is not an Ethernet. It relies on a subnet manager, a daemon that manage the network to find the best route for each communication. Okay, what time is it? Oh, I have to hurry, not fun. Do you want to take a break right now or do we continue? Because I have a lot of things to show you today.
Beno, we can continue
Okay,
till
thanks.
10 a.m. for local time.
Okay,
11 for you. Yeah.
okay, yes, that's perfect. Thanks.
Okay.
It's just drinking small water. And let's continue. So let's focus on the software side.
Beno,
Yes?
please, you can also slow down a bit. Yeah.
Yeah, sorry. It's just that they just gave me 3 days to show you everything. It's kind of difficult. Okay, I will slow down. I will slow down. So let's focus on the software side. Okay, so let's isolate one node. Okay,
Please, sir, I have a question.
yeah,
Can you
please go on.
come back with the Ethernet or the infinite and the infinite band? We are in cluster system. We have to use all of them, or we have to choose the infinite band or the Ethernet band.
No, you use both of them.
Both of
Okay,
them. Yeah.
yeah, it's because, well, the InfiniBand is not made. You can use just InfiniBand if you want, but
Just in, yeah.
it's going to be a very big pain, to be honest,
Yeah.
because InfiniBand is not made to deploy things. So,
Yeah.
uh, for example, if you want, well, anyway, just one thing: the BMC don't work in InfiniBand. So you still need an Ethernet to reach the BMC, at least. Okay, you can try to use the InfiniBand to do everything, but it's going to be a very big pain, to be honest.
Yeah.
What I recommend is you use the Ethernet to do the administration stuff, so to manage your cluster, okay? And in parallel, you use the interconnect to provide it just for storage and calculation.
Yeah.
Just for you to know, the interconnect is not mandatory. The Ethernet is mandatory. Okay, that's all. The interconnect is not mandatory. It really depends on what your user needs. For example, here at Ore, I have a bunch of users that use Blender. I don't know if you know Blender. It's a tool, it's an open source tool to do some kind of 3D movies, okay, to animate 3D stuff. And to do an animation, they are going to calculate each frame of the movie one by one. So you have 25 frames per second to do the movie. And each frame is calculated independently. And each frame is calculated on one server at a time. For this kind of calculation, they don't need an InfiniBand because they will not use the network. They don't care. But if you have some scientist that is going to do some physics on your cluster, most of the time they will split the calculation over multiple server, and they will need to use an interconnect to get performances. Okay.
Yeah.
Well, but honestly, it's not mandatory. It's very, very expensive. If you don't have money, don't care about the interconnect. Okay, just try to get 10 gigabyte network Ethernet. That's, I mean, for most of users, that's enough. And also, don't be fooled by the marketing guys that always try to sell users the top high-end interconnect. I mean, you will see that most of the users just don't optimize their code. So a very basic old interconnect, even on my side, for example, for my own cluster here, we have an HPC cluster in Bretagne. We just bought an old one, one that was already used, because it's more than enough. Okay, it was like 5 years old interconnect, and we bought it because it was not brand new, but it's more than enough. So interconnect is just for calculation, but you don't. It's not mandatory.
Yeah. Yeah. In resume, to infinite man is the is for the communication between the node and Ethernet is for the management of the node. It's
Exactly.
simple. Yeah. Is
As
that?
simple as yeah, exactly.
Yeah.
That's correct.
Thank you.
Also, you most of the time just use also InfiniBand for storage because
Yes.
Ethernet is kind of too slow. Okay,
Yeah.
so when you have an InfiniBand, you
For
just use it
storage.
also for storage.
Yeah. For storage also.
Yeah, yeah.
Thank you. Thank you very
It's
much.
again, it's not mandatory. It's for comfort, I would say. Okay, let's continue. So let's focus on the software side. So we will isolate one node and check what's inside. So first, you have the operating system. Linux, you will see that it's kind of always Linux on this kind of servers. Two main Linux branch, Red Hat and Debian. Debian, most of the time, you will use Ubuntu because Ubuntu is kind of very interesting for HPC. On the Red Hat side, if you don't want to pay for Red Hat, you're going to use CentOS. We will speak about CentOS later, but Red Hat just killed CentOS because they don't like it. So there is a new challenger. You will speak about that later. So inside the operating system now, okay, so let's open the box. We have the kernel running. So the kernel is kind of, well, the core of the system running. And you have a bunch of services running around the kernel, okay? Most of these services are managed by what we call system D. You will see it. And some of them are kind of alone. For example, your user's calculation, stuff like this. So these one are on their own, not managed by anyone. So For example, here, this is a bare metal network. We call it bare metal. It means it's a server with a kernel, services, programs running. That's all. If you use hypervisor, you isolate each operating system. So you have the main bare metal server with its kernel, and it's running an hypervisor with virtual machine. Each virtual machine has its own kernel. Okay, so it's full, I would say, autonomous operating system. And each virtual machine has also its own services running. So it's interesting, but it takes a lot of memory because each kernel uses memory. So at the end, you just spawn systems that use a lot of memory, and also the hypervisor will reduce the performances of things running inside the VM. Okay. So the new stuff is containers with Docker, Podman. Podman is much better than Docker, to be honest. But anyway, containers, you are going to use the same kernel than the bare metal server. You just create small boxes, small isolated boxes for services. So it's like the VM, remember? Sorry, where is it? It's like the VM, you can see here, but with container, everyone share the same kernel. So you have direct access to the hardware. And it's very interesting because it do not impact nearly nothing performances. So it's interesting to do some calculation. Okay. So they share it's just like that. So this is a system. Now let's focus on a service, on a process. So what is a process made of? You have the process executing. You have the main thread. Okay, we call it the main thread. This is really the core of the thread. You have the kernel state, so with the ID, so to communicate with the system. The memory of the process. Okay, so it includes the code of the process that is executing. You have the stack, that's static memory. So you have the heap memory allocated, etc., etc. And you have your registers, so you don't really care. And each process has an ID on your operating system. Okay, so for example, on my server here, if I do, I can see all the process running, and you can see the ID of each process here on the left. Okay. A thread is different from a process, and be careful with that. A thread is a segment of a process. Okay, so you have in a process you have one thread, it's the core, the kernel, the core, the stuff executing, and you have the main thread, and you have some thread. Okay, on the thread of a process. So if you have a process with thread, they share the same memory. So if I do a scientific calculation that is going to use one process that's spread into multiple threads, the thread has access to the same memory, all of them. So they can access directly to the same memory. However, a thread of a process cannot access the memory of another process. Impossible. Of course, for security reason. Okay. So my thread here can access the process memory, but I cannot access memory of other process. If I want to do that, I need to communicate. Simply, it can be directly in the system, it can be over the network, whatever. And that's what makes, for example, the use of the InfiniBand network. When you want the process of all the cluster to communicate, they will communicate and share, access the memory of the others using the interconnect network, the InfiniBand. So multi-thread calculation, most of the time you will see this technology on your clusters. You will see OpenMP, very simple one, but dangerous one, but simple. Okay, dangerous because users thinks it's very simple. It's very simple, so I just use it. That's all. No, it's not like that. When you use OpenMP, if you want to reach performances, you have to do some kind of tuning. Just don't use it like it's very simple. Pthread, more than you are managing your Cepheus thread. Dask is very common today. It's a Python-based multi-thread mechanism. And CUDA, well, CUDA, if you don't know, it's the GPU NVIDIA proprietary stuff. It's made to spread a lot of thread over the GPU. Okay, so it's kind of different here. I put it here, but CUDA is very special. And regarding the multiprocess calculation to spread data over the network, you have MPI, Message Passing Interface. This is the most common one in HPC. So it allows process to communicate over the network. And again, Dask, because Dask can do both. Sorry. Okay, Dask can do multiprocess, multi-thread, etc. And when you do multiprocess and multi-thread at the same time, because it's very common that you want to spawn one or two processes per server, and then each process spawn its own thread to use all the core of the server to optimize everything. We called it hybrid calculation. So it's used for scaling. Scaling means we want to increase the number of servers without losing too much performances due to the network. So we use hybrid calculation. Most of the time, it's a combination of OpenMP here and MPI. We'll use both at the same time to get the maximum performances. Okay, let's close this and close the box. And we have finished with the software. Well, considering the time we have, let's move on. And since I have a lot of things to share. Okay. So let's move to setting up an HPC cluster. Okay. And don't worry, we will continue this afternoon, and then you will have the whole day to do the practical session. So this part is how to set up a basic HPC cluster using only open source tools. Okay, so you can redo this at home in VM, on your cluster, on a Raspberry Pi if you want, everywhere. The first step is to deploy your management node. Most of the time, you're going to deploy it manually with a USB key or something like that. So let's focus on the management node. You need first to install the operating system. For standard HPC cluster, it's Red Hat, CentOS, or Ubuntu. You can see Debian sometime. Then you're going to configure the basic repository. Repository means where you store the package for the operating system. If I want to install a tool, it's inside a package. So I'm going to grab it from the repository. Okay, if I want to install Firefox, the web browser, there is a package called Firefox inside the repository, etc., etc. So you're going, after installing the operating system, you're going to configure the basic repository. Oh yes, I forgot. When you install an operating system, I strongly recommend you to install the minimal operating system. An HPC cluster is something difficult to secure, okay? If you each time you install things, you increase the surface of possible vulnerabilities of your system. So try to install just what you need, nothing more. For example, don't install a GUI on your server. You don't need a GUI. You don't need Firefox. You don't need whatever, okay? You can install them when you want to learn, when you want to practice. But on a production cluster, just install the very, very minimal to reduce the potential surface for attackants to break your system. So once you have configured the repository, you just set up the main the main interface over the internet. Okay, so NIC is for Network Interface Controller. Okay, so you set up the NIC interface and say, okay, my management node is going to be with IP address 10.10.01 with a subnet 16. Then you install the HTTP server. The HTTP server will link your repositories to the network. So it will allow other systems on your own system to grab packages and to install them. Okay? So it will link the repositories to the network. Configure the HTTP repository, so finalize everything, etc. So let's focus on what is an HTTP server. In open source, it's nearly always Apache or Nginx. Here we are going to use Apache because it's, I would say, the most common one. So the HTTP server is going to be used to provide kernel on initramfs for the PXE. We will see that later. It's going to provide repositories, package. It's going to provide auto configuration file because you don't want to have to interact when you want to deploy a node. It has to be automatic. It can be used to trigger script for EPXE file, etc., etc. Okay, so it will just provide over the network files over HTTP. By default, the file path for Red Hat on CentOS is var www.html. So everything here in this folder can be queried with HTML request. So you can use wget, etc., etc., to reach a file. Okay, you will practice that. Don't worry. Then I need a DHCP server. The DHCP server is also connected to the network, and it will provide everything with an IP. We will see that just after. And you need to set up at the end what we called a PXE stack, because PXE means pre-boot execution environment. It's how to deploy other operating system using the network. When you have an HPC cluster, you don't go with your USB key on each server and plug it everywhere and deploy the operating system manually. No. You don't have the time to do that. You will use the network to deploy the operating system. Okay? So we will set up what we call PXE stack. The PXE stack is composed of the HTTP server we have seen before, the DHCP server here, and a TFTP server. We'll call about it later. Also, you will want to install basic command line tools. It's handy. So IPMI, remember, we have seen that just before. IPMI tool to power off, power on, see the console, etc. Clush is to do some parallel command on all the nodes at the same time. wget to grab file, etc., etc. It's just what you want, honestly. So just install all of this. So the DHCP server, a few words about it. It's ISC DHCP. So it will provide an IP to all equipment over the network. For example, when you plug the BMC of a server to the network, the BMC will request an IP. The DHCP will provide an IP to the BMC based on its MAC addresses or something else. So the MAC addresses is, I would say, the identifier of a BMC. It will provide everyone with what we call the next server. Okay, so you will see that during practical session, don't worry, on the file name. So it means what the node should use to boot, to start. DNS, gateway, time, etc. So you don't care, we will see that later. So for example, if I want to define an host in the DHCP, I will say, this is my host, it's called login1, for example. So this is the host name of my host, login1. This is the MAC address. This is the identifier, okay, of my Ethernet card. Each Ethernet card has a very specific identifier called MAC address. All of your Ethernet card has one. The provider, the guy who sells you the computer, must provide them to you. You have to ask for them, okay? Be careful. Don't forget that. And you say, I want this host to have this address. Simply. The TFTP server, we are going to use the Facebook TFTP. Yeah, Facebook. Facebook also provides tools for sysadmins because they have a very big data center, very big clusters to manage Facebook. And they provide some useful tool on their TFTP server is very nice. So we will use it. It's open source, Facebook TFTP server. So Facebook, the TFTP server, it's kind of similar to the HTTP server. It's just that the TFTP is a very old technology that is compatible with everything. You can just don't use TFTP and deploy everything using HTTP, so the web server. But with some equipment, it's going to be difficult. With the TFTP, you don't care. It always works. So let's use it. Okay. So it's old, very old protocol. The file for Facebook TFTP server will be in var lib TFTP boot. You will practice, you will see that. And my recommendation with my own experience is to stop here. Don't go further. Just install this and don't go further when you want to deploy an HPC cluster. Also, do not configure anything on the network. No VLAN, no LACP, just basic plan switching network, okay? A flat network. Why? Because you want to check first if you can reach all your nodes, if you can reach all of your equipment, and if you can deploy the operating system on them. You will see that deploying the operating system is a tricky part. It's not always easy. It can fail easily. So you don't want the network to be a trouble in that part. You want to check first if everything is okay, if your hardware is okay, if you can deploy everything. Then you will come back to the network. Then you will come back to add more services on your management node. Okay? So my recommendation is to stop here. You have enough to deploy nodes. Ensure you can deploy everything first. Okay? So now we have our management node. It is ready to deploy over the network. So let's try to deploy few other nodes. And my recommendation is to at least try to deploy one node of each kind to be sure you can deploy everything before proceeding. So let's focus on the login node, for example. When the server boot over PXE or IPXE, okay, so at the very beginning, when your server is starting, it will ask, okay, it will send a discover stuff on the network and ask for an IP. It will say, hey, hello everyone. So it will broadcast to the whole network. Hello everyone. My name is on the MAC, provide the MAC address. My name is that, and I want an IP. Please give me an IP. So it's called discover. Then your DHCP server will receive this as everyone and send an answer, an offer based on its configuration. So, okay, I know you. Please use this IP. Okay. So, for example, it says you have to use 10.10.2.1, but it has to be confirmed. So again, the node will send a new request asking, okay, can I be 10.10.2.1? And the DHCP server say, okay, acknowledge. And that's all. It's finished. Now I know my IP, it's settled. The DHCP server has registered me, it knows me, we call it the lease. It's registered, so now I am known. And I can proceed. So now that my server, my login node, has an IP, it needs to deploy. Okay? The DHCP server provided an IP, but also few interesting elements. It provides an URL for something we call the next server on the file name. So the DHCP server, remember in the configuration, let's come back here. We have our host login, but we have also the file name, what should be started, and the next server, who should be used to be deployed. Okay. So blah blah blah. So now my server is going to deploy. It will grab a few files. Okay. So the kernel and the initramfs from the network. Okay. Then the kernel will boot on the node, on the Linux node. So everything, you can see here, everything is in memory. We still haven't written anything on the disk of login node, okay? So the node is booting the kernel, it has grabbed over the network, and it will request an auto install file because it has to be automatic. So the auto install file, again, through HTTP over the network is provided to the node. It will request it. Then it will request some packages to install the operating system. So the operating system is going to be installed now on the compute node using the auto installation file packages. In the packages, there is also a kernel. It will install the kernel on the disk itself. Then the node will reboot and it's installed. You have the operating system ready. As simple as that. Okay, well, not that simple, but don't worry, you will practice. Okay, so once you have deployed everything, you need to add more elements. You need to set up the DNS server. Okay, the DNS is not mandatory. It's just that if your cluster is big enough, you may probably need a DNS. If you don't need a DNS, you can use external DNS, the one from Google, the one from Cloudflare, whatever. But it's interesting to have a DNS inside your cluster that will just forward requests, unknown requests to Google or whatever. Okay. You have to set up a time server. It's mandatory. And this one is extremely important. You need to be sure that all your operating systems are time synchronized, because most of the tool will need it. For example, when you want to authenticate a user or when you want to authenticate the job scheduler, it is also based on time. If the time is different, the authentication will fail. Also, if you have a shared storage, what happened if not everyone has the same time? For example, you will have file like 1 year old written at the same time that file from 3, I don't know, whatever, it's just broken. So you have to be careful. So time server is mandatory. You can configure advanced network if needed. Okay. Also configure the interconnect if you have one. You will configure the monitoring. Monitoring means you want some sensors to check your cluster if the cluster is okay, in good shape, etc. On the job scheduler. Job scheduler is going to manage the job of the users. Okay. On users authentication, LDAP, stuff like this. The DNS. DNS, so we will use bind 9. It provides hostname resolution. So for example here, I want to ping Ion 0001. The DNS provided me Ion 001 IP is this one. So on the network, I will ping this IP. And on the opposite, my DNS is done. Okay, cool. On the opposite, I can ask who this IP belongs to, etc., etc. Okay. Where is it? Here. Start again. Here. Okay. So it kind of provide link between IP and hostname. Also on small cluster, it can be replaced by a simple host file that it can do the trick. You will see that during practical session. So files are here. Well, not interesting to see here right now. The time server, we are going to use Chrony. The time server is extremely important. Okay, it provides the same time over the whole network and ensure all equipment are synchronized. And as I said, it is more important than it seems. Okay, if you don't have the same time, nearly everything is not going to work properly. Authentication, I/O, database, monitoring, everything is going to be broken. Okay, so be careful. You will see that during training. I can go. The monitoring. Monitoring, well, it's important to monitor the health of your cluster. You want to check each day, each morning, how is my cluster doing? Is it okay? Do I have hardware failure? Do I have software failure? Anything. So important if you want a production ready cluster. Also, monitoring is important for your boss, because you will see that the boss like graphics, like to see, they don't understand the technique, but they want to see graphics. They want to see green light everywhere. Okay. So having a good monitoring is interesting also. So it's going to monitor the cluster, report metrics, error. It's mandatory on large cluster because you need some way to check the health of nodes. And as I said, it's shiny. Okay, a good monitoring is shiny. we are going to use Prometheus to achieve that. It's a very new tool. It's very powerful. And you will see it's kind of, well, it's not the simplest tool, okay, but it's very powerful. So you should focus on this one. The job scheduler, last one. The job scheduler is extremely important. It is like the orchestrator of your cluster, because your users are going to log in into the cluster and they will submit calculation job. And that's all. They will not interact directly with the compute node. The job scheduler is here to manage computational resources and share them between users. Okay, it will spread on launch job. It will report the job, etc., etc. So it's what allows multiple users to be on the same cluster at the same time. Okay, we are going to use Slurm, the most popular one. Okay, then in the following configuration, we assume that the network repository DNS and time are configured across the network. Okay, we will call it the core of the everything, because I cannot put everything on the next schema. So we will assume that all of this is already done. So you have all your services running here. Let's focus on the storage now. So there are two kinds of storage. You have the non-parallel file system. So if I have one data, it is stored at one place. As simple as that. Most of the time, it's network file system, NFS. We have the parallel file system, and these ones are very common in HPC. When I have one data, it is split in small parts on multiple servers. So it allows redundancy.
Bernard,
If one of the servers fail, I still have my data.
Bernard, there's a
Yeah.
question on the chat.
Can you code some alternative to Slurm? Yes, of course. Well, honestly, there are not a lot of alternatives to Slurm, because Slurm is, I would say, the biggest open source stuff. And all of the others I know are proprietary. There is PBS, Load Leveler. Load Leveler, I think, is dead. So PBS, I just know PBS on the other side, but PBS is proprietary. You have to pay for it. Slurm is, I would say, the biggest open source one, simply put. I don't know if he's answered your question. I don't know a lot of other alternatives, to be honest. Okay. Parallel file system, so we have Lustre, BGFS, CWDFS, GPFS, ClusterFS. Yes, there is a lot of ones, okay? So when you spread data, it's faster. It allows to have very fast storage, okay? Simply. With NFS, you have very slow performances. With parallel file system, you can use a lot of disk at the same time, so you have very high performances. So in the practical session, you are going to configure a basic NFS server that will export standard basic folder, so a home for all your users, so they have the same home over the whole network, and software for your software. You should avoid exporting the OPT. I have seen that a lot of time. It's dangerous. Don't export the full OPT software, the full OPT folder. Sorry, 2 seconds. I need to drink. I speak, and I need to drink. So, okay, so now the storage is ready. Now let's focus on the login node. The login node is a dangerous node, okay? As I said, it must be kept as simple as possible, because let's take an example. Let's consider the login node to be a castle, a fortress, okay? When you have the nice user and the nasty user, the pirate, the one who want to get into your cluster and do some kind of crypto mining to get money on you, okay? If we have a simple web server, for example, like Google, I don't know, every website, users just reach the server, grab the data, and go back, because the door is closed. Same for the nasty guy. What is difficult in HPC is that the gate is always open because your users are going to need to go to SSH into the cluster to, to upload their data, to build their code, to launch job. It means that the castle is open. And this is very difficult because hey, nasty guys are going to use that. Once they are inside, they will go everywhere, check for vulnerabilities, and try to break your security. And this has to be understood. The login node is the way to enter your cluster. You have to contain the users here. They have to be inside the login node. You have no choice because they need to be able to build their code, to launch them, etc. But you have to be sure that this node is secured. So keep it as simple as possible. So you can update it each day with security fix. You can make it understandable for you so you can secure it. Okay, be careful. So in the login node, you have the kernel. Sometimes you have a firewall, a software firewall embed, IP table, NF table, whatever, firewall D most of the time. You have some very simple securities like fail to ban. It's very funny. If you plug your server on the network, in 10 minutes, you will be attacked. I assure you, if you plug your server on the web, on the internet network, it will take less than 10 minutes to be attacked by someone. And it will be all the time after that. You will see. IP are from everywhere. Most of the time, it's from Russia, China. Well, most of the time, it's the IP are from here. I don't know why, to be honest, and I don't care. It's just that you're going to be attacked a lot. So be extremely careful with the login node. It's a very vulnerable stuff. You have to secure it. Okay. An interesting tip is to change the SSH port. Most of the bots that attack over the internet are trying to check the 22 port, the default SSH one. You have to change it. Don't use 22. If you can use a very high port like 7777, for example, it's cool. Okay, it's very, very nice. It will lower the attack a lot. But users will have some difficulties to reach it because it's filtered on many firewall. A small tip, interesting one, is to use the HTTPS port, okay, 443. If you don't have to use an HTTP server on this link, use this port. It's interesting because the attacking bot, will not understand what's going on because it's not an HTTPS server on the other side, it's your SSH one. And users can use this port. It's not filtered because you need to be able to HTTPS from everywhere. So this port is very interesting to use as an SSH entry. So login node is where your users are going to be. So be careful with that. Enforce limit, no swap, monitor, ensure always up to date. Okay, security first. Also on the login node, you're going to mount the storage and you're going to put the job scheduler submitter file. So users are able to manage their data and launch job. Okay, I have 15 minutes left. Okay, it should be okay. So let's check the compute node now. Okay, let's focus on the compute node. Again, you have the kernel, you have the computational resources, processors, GPU, whatever, FPGA sometimes. You have to install the absolute minimum here because you want to get the maximum performances. So make them light, okay? Nothing too slower or disturb calculation. You have to consider also this node as cattle. It means you have a lot of them and you don't care about them. You lose one, it's okay, it's standard. You don't care, it's cattle, okay? I lose one, I just replace the hardware, redeploy it, and that's all. Nothing wrong. It's okay. Again, on this node, you're going to mount the shared folder for users, okay, to have their data, and you are going to connect it to the job scheduler. So we will mount home on software and install the job scheduler to manage computational resources. So jobs can be launched on node. And you're going to repeat that a lot of time to deploy all the node. Okay, that's where automation is interesting. And then you have your cluster ready for launching job on, well, as root at least, if you don't have user authentication. You need to choose how to manage user, so you can use centralized, pool, or distributed, pushed. Okay. My personal recommendation, if you have a very, very small cluster for a small team, go with distributed. Okay, don't care about very complex LDAP or AD system. Okay, just use a script or Ansible, whatever, and deploy your cluster your user manually. If you have a bigger cluster with a lot of users, you have to rely on a centralized mechanism, LDAP, LDAP, AD, Active Directory, whatever. Okay. Just a small, I think it's the latest part before we finished with this morning. Just give me a second. Yes, it's the latest one. So what happened if a user launch a job? For you to understand, with the job scheduler, okay? There is some kind of queue, okay, where the job is going to be put. And the job scheduler will try to maximize cluster resources. Okay, so not having node doing nothing. So here it's an example with your cluster is ready. Here we have the time. Okay, it's a small chart with the time on the node range. So when you are at the top here, it means that you use all the node. The node range means all the node at the top. So if I use half of the node, I will be here. Okay, and here it's my job queue, where my job are put when users submit them. Then let's see what happened. I have users that launch a big job that takes some time and that use half of my node. Okay, so the job scheduler is going to say, okay, I have 3 resources, I start it. And half of my node are now allocated to this job that is running. In my queue, it's running. On it, you can see here it's running in my cluster. Then I have another users that launch another job. This one is smaller. It will use 1/4 of my cluster, but it lasts longer. The user requested resources for a lot more time, okay, for more time. Job scheduler checked, okay, I have 3 resources, it's okay, I can launch it. So it launched the job. Okay, so here I am here. Then I have, so you can see we advanced, the first job is finished, so it has freed now my node. I still have one job running, the long one, and I have a new user asking for a very, very big job using all the nodes of the cluster, but a short one. The job scheduler check, I don't have enough resources. You wait, so you have to wait. You are requesting too much resources. I cannot launch you because there is already one job running. You have to wait, so you are delayed. Then I have another user launching very small job, tiny ones. The job scheduler check, I have 3 resources. This one is waiting. I don't have enough resources. And I see that my job running that prevent the red one from running is going to take a lot of time. So I can launch the small ones. It's okay. I have time to do that, to fill the gap. So the small ones are launched. Then I have my first user launching again the same job, the big one. Okay, the tiny one are finished, but I am still on my long-term job. I don't have enough resources to launch the red one. So the job scheduler say, okay, you can start also. Now I have advanced again. Okay, you see, I was here and now I move again. And one user launch a very tiny one. Okay, but the job scheduler say, okay, stop. The red job, it has been launched, it has been submitted a long time ago. It needs to be run now. I need to allocate resources. So stop, we stop here. I don't launch any more small job because I know the big one is going to end, the very long one. I want to allocate this job. There is some kind of mechanism of priority. When a job has been delayed too much time, it will increase in priority, and at some point, the job scheduler says, stop, I need to allocate resources to save resources for this job. So the tiny one is delayed. and the big one is launched just after the long one, and the tiny one will wait because it needs 2 nodes. The tiny one needs 2 nodes. I don't have them, so it is delayed. I need to launch the big one. You see the mechanism? It's quite simple. It just tries to fill the whole cluster. Well, since we are at the end, I will just do the 5 minutes. I provide you all the practical session things, so you can start doing the practical session this morning. I will not be here after that, but today, and we will continue this afternoon. But right now, I need to just finish to show you the practical session. So like 10 minutes, and you can take a break. Few tips about HCL7 to HCL8. If you are in HCL7 cluster, the kernel is upgraded. The Python version is upgraded from 2 to 3. So all your Python scripts are not working anymore. You need to upgrade them to Python 3. Repositories are split into two parts. Rebase OS on application stream. I will speak about that just later. Package manager is a new one, DNF. Time synchronization is cronid now mandatory, and firewall is always firewall D, but it's no more IP table, it's NF table. So repositories are now in Red Hat on CentOS. You have 2 kinds of repositories, base OS and application stream. Base OS means it's just standard packages with 1 version fixed for the whole Red Hat. Okay, so for example, Firefox. I have Firefox 60, and it's base OS, it's a package, that's all. Application stream is different. It's some kind of package, but very specific version. Sometimes you need, for your production, a specific version of, let's say, PostgreSQL database. I want 9.6 version. It's mandatory for me. I need it. But some other users need version 10, for example. Red Hat provides a way to have, for all users to have what they want. Application streams mean Red Hat provide PostgreSQL on 3 or 4 versions of it supported, and you choose which one you want to install, simply. So that's what our application stream, okay? Well, you will not use that a lot, honestly. I just provide it here. When you have the PowerPoint at the end of the session, it's some kind of way for you to remember if you need it sometime, okay? So let's move on this. It's not very interesting for you. Also, if you want to manage network, no, it's called, you have to use NMCLI to bring up device up and down or to set an IP, okay? You will see that also during the practical session, don't worry. This is not interesting, blah, blah, blah. Okay, CentOS, about CentOS. If you know the Linux, Linux stuff, CentOS is a clone of Red Hat, but free of charge, with no support. Red Hat has been bought by IBM, and IBM is a money enterprise, okay? They don't like Red Hat to have some kind of competitor, a free of charge competitor. So Red Hat killed CentOS just at the beginning of this year. It was like a few months ago. So now if you want to use a Red Hat clone, you have to use Rocky Linux. It's brand new, like few days ago. It's fresh new. It has been released a few days ago. So I didn't have time to update the practical session. So the practical session is still based on CentOS. But now you should migrate to Rocky Linux. Red CentOS is dead. At the end of this year, CentOS will be deleted. Last tip for this part. My recommendation is that knowledge comes from interacting with other sysadmin. Don't stay alone, okay? HPC is a fun world, but you have to share with others. You have to meet with others. I don't know if there is an African mailing list or exchange channel for HPC expert. Try to exchange a lot. It's what makes this job interesting. And it allows you to learn new technology. It allows you to learn security stuff, etc., etc., etc. Okay, very important. Don't stay alone. Okay, practical session. Time to dive in. So here are the link to the practical session. You can find it on the web. I created a small one here. It's lighter than the big one. So please write it down right now. cpcx.cx/u big V9. And I've written a whole practical session for you today. So please, it took me time to do that. It's something that takes time. So please take your time to understand all configuration file. Investigate, test, modify, browse the web, whatever, but don't rush it. Try to understand how it works. It allows you to deploy manually the most standard cluster ever. Okay, but at least it works. So it's a strong base. The practical sessions are asynchronous. I assume you will start after your break today, and this afternoon I will be here to answer all your questions, and you will continue to do the practical session. I will be here to guide you, to answer questions, to show you things, etc., etc. Okay. I know that you have been provided VM, virtual machine, to do the practical session. So it should be very simple. Let me show you the practical session. Where is it? Here. Here is what it's look like. So you have some kind of summary here of everything you're going to see. Well, don't be impressed. It's very simple. Don't worry. Okay. So basically, you will do everything we have seen today in the presentation. A small vocabulary part, cluster description. We are going to set up the management node. Okay. So we will deploy the management node with everything we need, the HTTP server, DNS, host file, time saver, and the PXE stack. I described how to do it. I mean, everything autonomous. You don't need external proprietary packages. You will build everything yourself. Try to understand how you build things to be able to upgrade version later. Okay. Then you will deploy the other node. So for what I remember, you have one management node and two VM were provided for you. So in the TP, in the practical session here, I was expected 5 VM, but you have 3 of them. That it's more than enough. Okay. So you're going to use Odin, your management node, so one VM. You will deploy the two compute nodes, Valkyrie 1 and Valkyrie 2, and consider that Thor and Heimdall are the same as Odin, so merge the 3 of them. It's okay. For small cluster, it's very common that the management node is also the login node on the storage node. Okay? So merge the 3 first one, Odin, Thor, and Heimdall. Consider that Odin is also Thor, is also Heimdall. So remove in each configuration file Thor and Heimdall. Replace them by Odin. Okay? Because you only have 3 VM. What is important is that you have 2 compute VM to understand how they work. So you're going to deploy that over the network, configure the storage, do the Slurm, job scheduler, submit some job. That is the fun part. You're going to submit some jobs. So I wrote that because you will need to show your users how to submit a job. So you need to learn how to be a user, in fact. So you will submit the job yourself here. Oh, I did an issue here. I will correct that just later. Add user, small few part about the InfiniBand, and I forgot, I will add that during this afternoon. I forgot how to configure the NVIDIA GPU part. I will write this afternoon quickly, okay? Once you have finished the practical session, I think you should take a break for the day. Take the time to compute everything into your head. It's a lot of things. So take the time to compute a lot of things. Don't rush next day part, okay? Manipulate, have fun with all of this, okay? I will be back at, so right now it is, for me it's, for you it's 10, for me it's, well, this time I need to go to school, take the children. So I will be back at, so for you it's at 1 p.m. Okay, so I will be able to answer all your questions at 1 p.m. Thank you for this, for following this morning, and have fun with the practical session. Any
Okay.
more questions before the practical part?
Yes. So Benoit, you said you'll be coming back by 1 p.m. your time. That
2 p.m. my time, 1 p.m. your time.
1 p.m. Okay. Okay.
Hello, Bernard.
Yeah. Hello.
Yeah, I just want to call your attention to something regarding the VM we created for the participants. The Pixie boots will be picking from a DHCP server that they are all connected to, as in all the VMs will be picking from the same DHCP server.
So
So there
the
might
virtual.
likely be a problem because from the head nodes, I think individual again will have to create their own DHCP server. So there might likely be some complexity along the way, or so I don't know. What do you suggest? Do you get my question?
Yes, I understand. You mean that all the VM are sharing the same private network, right?
Yes, all the VM are connected to the same private network.
So each user, I mean, I was thinking that each user have its own private network for its 3 VM, but in fact, no, they all share the same
Because
network, right? Okay.
in the first instance, everything will be okay, but when they start configuring some other things on individual node, there might likely be problem.
I see what you mean. So you mean that?
Except maybe for the DHCP, they won't have to configure anything that has to do with DHCP in the practice. I think with that, I believe we should be able to manage the problem that would have been created.
Yeah, I think so. So for what I understand, you have today this 1 VM, 2 VM, 3 VM, and if each user, you see my screen? Yes, yes. And each user is connected. So I was thinking that each pool of VM are isolated. And what you tell me is that it's not the case. Right now, the other
Yeah.
VM are also connected to this one. Yeah, okay. Maybe what could be interesting, you don't have your own DHCP on this part, or do you have your DHCP already running?
Like each, come again with your question.
On your side, for the hypervisor, do you have a DHCP running also on this network or not?
Yes, there's a DHCP running.
Okay.
So it's the DHCP that all the VM that we Pixie boots will be picking their IP from. So they're all sharing the same DHCP server.
I think it's okay as long as you show them how it was configured. Well, I think it's okay. If the idea is for everyone to understand how the Pixie process works.
Exactly. That will be
So
achieved.
yeah, I think it's okay. Just be careful then, everyone. Don't start your DHCP server. Don't start your DHCP service. So this part here, when you install the DHCP server, do not do that.
Probably they should not even install the DHCP server. That's my suggestion. At least they should just leave that and do every other thing, if it's possible.
Yeah, they can. I think you should skip the DHCP part. Okay, the topic is at least you show them how to deploy over PXE, and then they can continue with everything else.
Okay. So
okay, that's cool.
Yeah.
Yeah, sorry, I didn't explain well. Okay, then I will be back at 1 p.m. for you to answer your question. Then don't hesitate at this moment.
Okay. Thank you so much.
You're welcome. Bon appétit. it's early for you, not for me. Bon appétit, and see you soon. See you later. Thank you. Oh, I have one question. The scheduler can only use the number of non-request instances. It cannot know how long a task is. Oh, good question. In fact, the scheduler knows how long a task is because when you submit a job here, when you submit a job, you request a time slot to the job scheduler. So the job scheduler is basing on that to allocate resources. Okay. No other question?
Hi, Benoit. Um, yes, but the user must provide this time, but if he is wrong with this time, this can fail a good management.
Well, if the time is wrong, if it's if it's bigger than expected, then the job will end when the script end here. When the script reach here, the job stop. Okay, that's all. So if the user asked for 10 minutes and the job took 5 minutes to complete, then the job is finished and that's all. If the users ask 10 minutes and at the end of the 10 minutes the job is not finished, the job scheduler will kill the job.
Okay.
Simply.
Thank you. Okay.
You're welcome.
Thank
You have
you.
to be careful.
Okay. Yes, of course. Okay.
No other question?
No, that's it.
Okay, cool. Then see you this afternoon. Thank you for following this first part. I will try to grab a webcam for this afternoon. See you. Bye-bye.
Thank you.